Okay, so the last thing we have to do in this unit is really talk about how do we solve some of these problems involving circular motion. Okay, so it's going to be kind of applying Newton's second law, right? And so we're still studying Newton's laws of motion here, right? We're just looking at the circular aspect, right? So again, we're going to focus on our 3 steps: draw, sum, solve. Okay, and remember, circular or centripetal force is a net force. So when you apply that, it's just going to be mv squared over r. Okay, now specifically here are the steps for circular motion. First thing you do is you're going to draw a free body diagram, okay, just like we did when we did linear motion. And so what happens is draw a vector, and then once you near the free body diagram, you're going to draw a darul, okay, a vector showing the acceleration object pointing toward the center of the circle, just so you can identify, because the center of the circle is your positive direction there. And then you're going to sum the forces in the circular and non-circular direction. So this is a little bit different, right? And I told you in the last video that the circular direction is basically the x direction, while the non-circular direction is basically the y direction. Okay, and then you're going to solve for what you're looking for. Okay. Now some of these problems they're not gonna give you the velocity, right, that the object will kind of rotate at. So you have to calculate it. We talked about this in the Ferris wheel question in the last video. And so it's just going to be 2 pi r over t. And so the way to think about this formula is that you're traveling the circumference of the circle in the period, okay, in the time given to you, and this time is known as the period. Okay, and we want to know how this works? Look at the Ferris wheel question in the last video. Okay, and so we're just going to kind of do some quick problems here. And so we got to derive an expression for the speed of a satellite that goes around the Earth at a height h, and the mass of the satellite is m, and the mass of the Earth is capital M. Okay, and so what happens really here is that so if we're in orbit, right, we are experiencing the gravitational force. Okay, in fact, let's call this R and not D. Okay, so we're experiencing the gravitational force, but what is causing this gravitational force at this point in time? Well, it's just the circular motion. Okay, and so what we're going to do is just simply solve this now for V, right? The m's are canceled. This m2 will be the mass of the planet, and the m1 will be the mass of the satellite. And so we end up with v squared over r equals g m2. Okay, we'll just start plugging in our variables that they want us to solve for. Okay, so the g big M over r squared. Okay, and what can happen here is that one r on the left-hand side cancels another r on the right-hand side. So that r cancels one of these. And so now if I simplify, I got v squared equals g m over r. And then the last step, take the square root. And so v, the speed of a satellite, is simply the square root of g m over r. Okay. In fact, it's going to be the square root of g m over the radius of the planet plus the height. Okay. And remember, so this, we talked about it a couple of videos ago, this is what we call orbital radius. And remember that the gravitational pull, it comes from the center of the planet. Okay. So for this problem, we're looking at a coin placed on a turntable. Right, a turntable is essentially a record player. It slips when the speed goes greater than 50 centimeters per second. And the question is, or there's two of them. What force is providing the centripetal acceleration when the coin is stationary relative to the table? And then what is the coefficient of static friction between the coin and turntable? Well, the second question kind of gives away the answer to the first one. Okay, in fact, it's going to be static friction that is going to provide the centripetal force. Remember that centripetal force is not like friction. It's not like weight, right? It's what causes this is a net force, right? Or what causes a net force, okay? And so we got to treat this like it's a Newton's law problem. So we need to do our free body diagram, okay? So we have, again, normal. We have weight down, a normal force up, okay? Now, when it talks about slipping, okay, slipping really is what we kind of want to provide it from going, or prevent it from going in. So our frictions are going to be out, right? And so our acceleration, so here's our turntable, here's our coin, right? Coin is round, sorry. Okay, so the coin, once it goes past a certain speed, right, it's going to fly off, okay? And we want to prevent that flying off, that slipping out, okay? So in actuality, the friction, sorry, will go the other way, right? Because we don't want it to go out, okay? We want it to stay on there, so the friction has to act against the motion, which is going to be to the inside, right? And so basically, we're going to label it X and Y, but what it really boils down to is circular and non-circular, right? So the X is our circular or circle motion, and the Y is our non-circular motion. And that's one way you can think about when you're doing these, okay? But if we just keep it the way it is, right? Friction lies in the X, and everything else lies in the Y. Right, and so we're going to do sum of the forces in the Y direction, 0. Right, what forces do we have acting? Normal and weight. And so our traditional solving in the Y direction, right, where we find that normal equals weight. Now we go over to the X direction. All right, sum of the forces in the X direction is equal to MA. Okay, but remember, A is B squared over R, which is our centripetal force, okay, or centripetal acceleration. So we have F equals MA, and we have F equals mv squared over R. I'm going to come over here to where I got more space, okay, and so we keep just plugging in now. So we get F is mu Fn is mv squared over R, okay, but we found that Fn was mg. Right, and so masses cancel, and so you've got mu g equals v squared over r. Now, if you remember when we did Newton's laws, we talked about acceleration of a sliding object. Well, there it is right there. Okay, acceleration of a sliding object is mu g. But what we're going to do, what we're solving here is for the coefficient. So we end up with mu equals v squared over gr. And now we just plug in our values. So it says at 50 centimeters per second, or 0.5 divided by 10 times, and it gives us a radius, or where it's placed, of 0.30, right? And we find that the coefficient of friction is 0.083. Okay, so the coefficient of friction between the turntable and the coin is 0.083. All right, so here's the last problem for this unit. Okay, so it says here, use circular motion driving expression for the force exerted by the Earth on the moon. Right, and so here's our Earth, here's our moon, right? And so the moon is in orbit around the Earth in a near circular pattern. And so if we're using, excuse me, if we're using force, we're going to use our centripetal force, right? Because it actually tells us to use circular motion to derive this equation. And so, and this, the mass is the mass of the moon. And so if I plug in, and remember, if we have an object going around in a circle, and it takes a certain period to do that, This is our equation, and that should be a capital T. Let me fix that. And, remember, time period or period is capital T. And so we just plug in our values, or our expressions. So we got M, right, the mass of the moon. V is now 2 pi r over t squared over our radius. Okay, and remember the radius is really the distance between their centers. And so we get M, and we square all this. So it's going to be 4 pi squared r squared over t squared divided by r. And now we just kind of do a little bit of algebra. Right, we're going to bring this t squared down. We have an r in the denominator. We have 2 r's in the numerator, so that's going to go away. And so this is going to end up being 4 pi squared mass of the moon, right, because it's the object in orbit, divided by, right, times r divided by t squared, right? So this would be the speed of the moon. And what we could do, or what they can do in the problem, is now actually give you the mass of the moon, how long does it take, how far is the moon away, and then you can actually calculate what's the force that the moon experiences between us. And we can also go back and compare it to the gm1 m2 over r squared version, because they said to use circular motion, okay, to find this expression. So that's it for this unit, okay? And then we'll get the next unit, unit 4, is going to start talking about work, energy, and power, which is a big topic here in AP Physics 1.